This is 10.8 vectors. So we're reaching the beginning of the end. So vectors appear a lot in physics, and you're gonna see them a lot, especially if you're gonna have to take either physics 125, physics 180, even if you're taking physics 185. All the different types of physics, you have to use vectors. Let's start off with the definition of a vector. So a vector is just a mathematical object that has both magnitude and direction. So those are basically the two key things that kind of characterizes a vector. So they are heavily used in physics and engineering. So let me give you an example. So if I were to say that a car is going at 60 miles per hour, that's not a vector, because even though I am given the magnitude, which is 60 miles per hour, it doesn't tell you anything about the direction of this vector. Okay, but if I said this car is going 60 miles per hour southwest, then it is going to be a vector because it specifies both magnitude and direction. So if I only have just the magnitude itself, then you just have something called a scalar. So a scalar only has magnitude, whereas a vector has magnitude and direction. So if you think about some examples are velocity, force, displacement, spin. So these are good examples of vectors. And the way that we kind of denote vectors, we kind of bold them, but when we write them down and we do problems, it's really difficult to bold. So you can write UVW, or you can just write little arrows on the top. So usually you can write them like this, V, W. That just means the vector U, vector V, and vector W. And you'll see vectors a lot. You'll see them again in pre-calc. You'll see them in physics and engineering, and you'll see them in Calc 3. So if you go all the way to Calc 3, then you're going to see them a lot. If any, the entire course is just vectors. So basically, if you're given two different points, so let's say you start off with a point P and a point Q. Let's say that's where you're ending it. So a vector can be represented as PQ. So let's say in space you have a point P and a point Q. Then basically you can represent this vector like an arrow. Okay, so this is how we have a vector. So it has a initial point, that's where it starts, and here is where it ends. So that arrowhead on the top indicates that it's going to be a vector. So it's a direct so it's not a line, it's a directed line segment. Okay, so imagine that this is where it's stopping. Okay, so how do we create and graph vectors? So the order in this case matters. So you basically subtract two different points from each other. The ordering in which you subtract the points does matter, because if you subtract it the wrong way, then basically what you're going to have is a vector pointing in the opposite direction. So you might have it opposite. So you have to be very careful with that. So if the initial point is P, and P has a coordinate of x1, y1, and the terminal point is Q, and that Q has x2, y2 as its coordinate, then the resulting vector is as follows. So you basically take x2 minus x1, and then comma y2 minus y1. So the way that you kind of create the vector, you draw like these little brackets, but they're kind of pointy brackets, and then you just subtract the x coordinates. So there's the differences between the x coordinates. So basically it's terminal minus initial, so wherever it ends minus where it started, and then y2 minus y1, which is basically the ending and the starting. So that's kind of how you create a vector. And then we'll go ahead and I'll show you how to graph these vectors in a little bit. So the first thing is consider the vector whose initial point is 2, 3 and terminal point is 6, 4. So find the vector and graph it. So first we want to find the vector PQ, and we're going to write PQ like this with an arrow. You don't need to write it with two different arrows. You can write it like that, or I usually just tend to just write it like this. So we want to be able to do this. So let's go ahead and subtract them. So the terminal point is 6. So I'm going to take 6 and I'm going to subtract it by the initial x point, which is going to be 2. And then I'm going to take comma. The terminal point was 4, and I'm going to subtract it by 3. So 6 minus 2 gives me 4, and then 4 minus 3 gives me 1. So this is basically going to be my vector. So how do you graph it? So let's just do my x and y plane. So we're going to start off with P. P is 2, comma 3. So there's the point P. And then, let me write P. And then our other one is Q. So we're going to go to 6. 1, 2, 3, 4, 5, 6. And then go up to 4. So 6, 4. This is point Q. So this is going to be my vector. Okay, so there's the vector itself. Okay, so there's the graph and there's the actual representation of the vector. And you can kind of see that in the x direction, this vector is moving 4 units. So it's going from 2 to 6, so it's moving 4 units over, and then it's going up 1 unit. So you can kind of think about it as slope. Okay, so over 4 and then up 1. Okay, so here we have a vector is a standard position vector if its initial point is at the origin. So can you graph the standard position vector for the previous problem? So this vector is not in standard position because it's not at the origin. So you can kind of draw this vector so that it starts at the origin. All you gotta think about is, okay, in the x direction, I gotta move 4 units over. And in the y direction, I gotta move 1 unit over. So basically, this vector that I just created is the exact same vector as this guy. Okay, all I just did was basically moved this guy. Imagine that I'm grabbing this vector and I'm just putting it at the origin so that its tail is right at the origin. So I'm just moving it over. So, but I didn't change anything about the vector. I didn't change the direction. I didn't change the magnitude. I didn't shrink it. I didn't do anything with it. I just moved it. So these vectors are equivalent vectors. It's just that a standard position vector is much easier to work with when it's at the origin. Okay. So that's basically what it is. So vectors can be moved around as long as you don't change the direction and you don't change the magnitude or the components themselves. So the components are the x's and the y's. So the differences. So these are what we call the components of the vector. If you have a vector v that's equals a comma b, a and b are what we call the components of the vector, okay, which is just what I just said. So you can also find the size of the vector by finding the magnitude as well as find the direction. So if you want to find the magnitude, this is how you find the magnitude. So we just went over complex numbers and polar forms. So it's basically the same thing as finding the modulus of it. So take the square root of a squared plus b squared. So basically this is how you find the magnitude, and usually the magnitude is just with an absolute value. Later on there might be different ways to denote magnitude. Some people will write 2 different lines to denote magnitude. So just keep that in mind. So that just tells you how large this vector is. If you want to find the direction, theta is just equal to the inverse tangent of b over a, which b is kind of like the y coordinate if you kind of want to think about it, and a is going to be the x coordinate if you think about it that way. So these vectors have a lot of tie-ins with complex numbers, and if you think about it, it's kind of the same as a complex number. So, but now we're just in a different plane. So 2 vectors here are going to be equivalent if they have the same magnitude and direction. So the direction and the magnitude are the same, then they're called equal. And additionally, they are equal if they have the same position vector. So if you were to have 2 different vectors in space, right, one over here and one over here, they kind of look like they're the same. If I were to take these vectors and place them at the origin, and they're exactly the same, then they're also equal to each other. Okay. So so here, let's do an example. So find the magnitude and direction of the vector with initial point P -3, 2 and terminal point Q -2, -4. So let's start off by writing the vector itself. So let's call this vector PQ. All right, so first let's try to draw the vector. So the terminal point is -2, so we're gonna start at -2, subtracted by the initial point, which is gonna be -3. And then you're gonna have -4 minus this 2. So that's going to give me, what is this? So this is going to give me a positive. So that's going to be a positive 1. And the other one's going to give me a negative 6. So this is going to be my vector itself. Now, we don't want the vector. What we want is the magnitude of the vector. So the magnitude and the direction. So the magnitude itself is going to be the absolute value of PQ. That's going to be the square root of the sum of squares, which is 1 squared plus negative negative 6 squared. So that's going to give me 36 plus 1 gives me 37. So square root of 37 is basically the magnitude. So we're going to leave it like that. And now all we got to do is figure out the angle. Okay, so theta in this case is going to be tangent inverse of b over a. So here b is negative 6 divided by 1. Okay, so let's get our calculator. Put inverse tangent of negative 6, I'm going to get negative 80 degrees. Negative 80.5 degrees. Now we have to be very careful because where exactly is this angle? So if you think about 1 and then negative 6, then the vector is going that way. So one way that you can kind of think about the direction is that this is an acceptable answer, but another way that you can do it is just adding 360 to make it positive. So if you want to just add 360 degrees, then it'll be 279.4 degrees, or 0.5 degrees. Okay, so this will be the direction. That's basically how you would find the magnitude and the direction of this particular angle, this particular vector.